Earth and space and high-speed search. And this of what you and I'm also talk about how your own job by being an entrepreneur, why you might consider graduate school, and then just little bits of career advice that I've gotten throughout my career. The picture that you see here is a Smith chart quilt. It's a large quilt that's up on my wall. It's a Smith chart. I'm sure you recognize it. My students sign this quilt when they defend their thesis or their dissertation, or when they do their senior design project with me. Let's talk about communication first. 5G comes up all the time, and 5G is about more and bigger data, what you're able to send and where you're able to send it. This is a technology that's the next generation for our communication, and it's very important, and it's going to give us a lot of new opportunities. One of the most interesting of the 5G opportunities is actually that it's going to make the latency or the delay between data packets be so much lower. Now imagine what you could do with that. So for example, if you were doing medicine and you were able to send data virtually instantly, you'd be much more effective in being able to guide a doctor in a remote location from a doctor perhaps in a large city. So there are many opportunities for 5G data that we are just starting to realize might be possible. Drones is another of the very cool and modern applications. Amazon recently received permission in the United States to be able to deliver boxes or packages by air. This is one of the pictures of the possible drone applications. They're not quite delivering yet, but they're starting to experiment with this. So it's going to be pretty exciting when I get my first drone delivery on my porch. I think my dog will probably bark a lot. This is some work that I did for my PhD. It was the analysis of the fields in the human head from a cell phone. Now, these phones at the time were at 915 megahertz, but 5G is going to be much higher frequencies than that. Now, higher frequencies make the fields so that they are much more concentrated, but also they don't penetrate nearly as deeply into the head. These are going to be different effects and interesting effects, and we'll be studying those too. Now, and 5G is exciting because you can have more and bigger data, but this is my road. And we're high in the mountains in a very rural area, only 15 universities, but originally there was no internet at my house, none, like not at all. See the mountain right here, this little mountain peak? That's where we built our internet station for our neighborhood. And this is how we did it. I have a horse, we carried top of the trail, all of the neighbors helping together to build an internet base station that went line of sight 12 miles away to a neighboring city. You can see that it's solar powered, and in our snowy climate, it's a bit challenging. So the fact that I needed to turn off my video tonight is not too surprising, considering that this is the extent of my internet. What I would like to do is challenge those of us in electromagnetics and wireless to seriously consider not only the large data applications of the world, but also the regions that have no internet at all. So the United States has areas that have internet or very poor internet. I'm sure that you have some in India. People are not able to access education, medical care, and basic internet as we might expect it. So let me challenge you to seriously consider what are the opportunities for being able to get internet in a cost-effective way to rural areas. This is another of the challenges of our time that has been heavily observed because of COVID and the need for education to go online. Now let me talk a little medical applications. Electromagnetics have several properties. One of the properties is they transmit, reflect. This is a breast model from Susan Hagnes at the University of Madison, Wisconsin, and there is a tiny tumor inside this model. The idea is that fields from the outside will reflect off tumors which have electrical properties different than the rest of the body to find them. So medical imaging of many different kinds is done with electromagnetics. Here is another imaging application. This is a head, and we made several different antennas for MRI. Now, in MRI, you go inside a very large magnet and it polarizes the cells inside your body. Then the magnet releases and the cells bounce back to their normal location. The antennas that you see here actually pick up the magnetic fields, electric and magnetic fields, as your cells return to their normal position. Now, in a typical MRI, you would have a large coil over your entire head, and it would give you a really good image of the head. However, if you wanted to be able to zoom in on really detailed areas, this particular set of antennas was actually designed for the optic nerve. If you want to be able to zoom in on that, you need to be able to have antennas that are even more deeply focused. And that was what this specialized array was designed for. So even though we have exactly the same hardware and exactly the same MRI, we can get a much better picture of a very small region of the head. It doesn't do a great job on the rest, but it does a really good job on the optic nerve. So being able to design a specialized head coil was pretty cool. Now, the Internet of Things is something you've probably heard about as well, IoT. Let's think about the Internet of medical things. So what things can be connected to the Internet that may have different applications? I'm going to show you several implantable medical devices, and each one of these could potentially be connected to the Internet to be able to upload and download data. If you have a cardiac pacemaker or defibrillator, as you see in this picture, there is a battery pack. See right here where it says pacemaker? That's where the battery is. And then out of there comes a lead, an electrical piece of electrical wire, and it's connected into the heart. The pacemaker sends a shock. It literally is a pulse shock that shocks the heart to keep it beating. That's a pacemaker, or to start it beating properly. That would be a defibrillator. So this is the standard pacemaker today. A new design right here is a leadless pacemaker, which means the battery and everything is actually implanted inside the heart so that you don't have to have this big long cable. Very cool device. So pacemakers are one of the things that are implantable medical devices. Now here's an artificial pancreas. That is for someone who has diabetes. So they have a glucose sensor right here that you can see. And then on the belt, they have a control algorithm and an automatic delivery insulin pump. Now, the automatic insulin pump is actually plugged into the body. There's a needle and wires that go to the body. So the glucose sensor sends information to the control algorithm, which pumps out a certain amount of insulin, and then you can monitor this, or the monitoring can be sent to your doctor. This is artificial retina. It helps blind people see. There is an electrode array that's implanted in the back of the eye that will stimulate the optic nerve and be able to help that person see when otherwise they are profoundly blind. There's a camera and a transmitter outside. So the camera right here on the glasses is what's picking up the visual image. The transmitter sends the signal to an electrical system inside the eye, and then the electrodes stimulate the optic nerve to help the blind person see. Now, there are several aspects of electromagnetics here. One is going to be the antenna inside the eye, another is going to be the antenna in the transmitter, and then a third aspect of this are actually the electrodes and how they interface with the optic nerve. The cochlear implant is a similar and very interesting device. This is to help deaf people hear. Again, you have a transmitter that's picking up sound and sending it inside the ear, where it actually goes into the canal of the ear, and each of these little blue spots are electrodes that stimulate the nerves inside the ear to help people hear. And again, we have transmission that we need to go from outside the body to inside the body, and that's a major electrical magnetic challenge. Deep brain stimulation is one of the newer applications of these medical implants. They use the same Pacemaker, and a very similar lead, as you can see, comes up on top of the head, and then it goes to an electrode that is implanted deep within the brain. Now, each of the areas that this electrode may be implanted can be used to treat different types of diseases. For example, Parkinson's disease has been one of the most effective treatments from deep stimulation. Essential tremor, epilepsy, dystonia, which is a problem with walking, medical depression, and many other psychological disorders. Depression is an area that I find particularly interesting and have been working on recently, and that's where the deep brain stimulation is used for depression, where antidepressants or medicine are ineffective. The interesting aspect of this is that sometimes this works brilliantly and the person feels much better, and other times it doesn't do anything at all. So it's very inconsistent. The aspect of that electromagnetically is that depending on how appropriate the stimulation is, you may or may not be able to treat the depression. And in many cases, it's difficult for the doctor to know because I can't actually see what's going on inside the brain. And I'm hoping that we will be able to image this in the near future. Here's a picture of the Utah electrode array. It's routinely used for nerve and muscle stimulation or recording. You can see that there are 10 electrodes along each side for a total of 100 electrodes over a very small region. This can be pressed onto the brain or the nerve for stimulation, that's where we're sending electrical signals, or for recording, where we are receiving the electrical signals for the brain. This particular device is used for both. It's used extensively in both research and treatments. So there's a lot of wireless technology in all of these medical implants. The wireless technology is used for two major things. One is telemetry. That's where you transmit or you receive data. The other is for wireless power transfer. Now you can imagine why both of these would be needed in a medical implant. Wireless power transfer, of course, is used to refill the battery or recharge the battery that's buried deep inside the body. The telemetry, we can imagine why we might want to transmit data, but we also want to receive. In the case of all of these implants, the electrodes are not only transmitting data, but they are receiving signals back as well. In the case of a pacemaker, for example, it's going to receive information about how well the heart is beating, and that's going to be used by the doctor to change the nature of the pulses that are sent to control the heart. So telemetry is normally both bidirectional, and wireless power transfer is from outside to in. Now, most of this is done today with inductive coupling. I'm familiar with that and have learned about this in your classes. That's where you have two coils, and the first coil has a current generated in it, producing a magnetic field. The magnetic field is picked up by the second coil and generates a current that goes back to the device. This is done for both telemetry and for wireless power transfer. Most of these coils are working in the kilohertz range, say about 18 to 300 kilohertz for their synchronization. So here's a picture of inductive coupling today, and let's think about the limitations that you can expect. If you have these two coils, you know the magnetic fields are closed field lines, or basically circles. So the further away you move these two coils, the less magnetic field they are able to transmit between them. So distance is a serious problem. In most cases, we can only go a few centimeters for the sizes of coils that are used in medical implants. Alignment is another problem. As soon as we misalign these two coils, we're going to lose a lot of the magnetic field, and our coupling will be much less efficient. Frequency and data rates are quite limited with inductive coupling, and efficiency, which includes loss in both the coils and the circuits, and I should mention also the body, is a serious limitation in this type of communication. Now, the art is flat and printed, such as the one that's shown here, with so many turns. We know that the more turns we have, n turns, is going to increase the amount of field that can be both transmitted and received. So these flat printed coils are very popular for medical implants, as are coils that are just wound up. There's also a really cool coil that you see down here at the bottom that's very tiny, that's printed on a square block of insulator and can be as small as 1 millimeter square. Now, 1 millimeter square is great for medical applications, but it's really difficult to align. So we have advantages and disadvantages as we make our coils smaller. Now, let me mention a bit about how I got into the medical field. Sam was a student in my class. This is actually his pacemaker. He missed class for replacement surgery because at the time there was not enough communication to be able to reach power was left in his battery. He wanted better communication with his pacemaker, so he didn't have to go to the doctor all the time for updates. His big challenge was he was a climber. He loved to climb rocks like this. That's not a picture of Sam, but it's like to do, which meant he would be very strenuous and his heart would need to beat very hard in order to support his muscles while he climbed. But then, if he was to sit quietly in my class, his heart needed to beat quietly and slowly. So he needed to calm settings on his paper, which he could not do at the time himself. He had to go to the doctor to have this change made. Today, most pacemakers will actually adjust to how much exercise you are doing so that you more appropriately. Sam did his senior design project working on our. So this was the pacemaker project. There's the pacemaker. It's about 2 to 4 centimeters in size, depending on the pacemaker and how it's going to be used. Now we can imagine that we might like to be able to put a half-wave dipole on this. So instead of using inductive coupling, we actually wanted to use wireless transmission, such as using an antenna. If we had a half-wave dipole antenna, the trouble is that if we had a low enough frequency that we could get through the conductive tissues of the body, the antenna would be pretty big. If we made a high enough frequency that the antenna was small, it would go very far in the body. So what we did is we miniaturized the antenna by taking a half-wave dipole antenna and coiling it up. As you see, we twisted it up, and then we put a ground on the end. That made the equivalent of a virtual antenna, so this antenna lasted approximately twice as long as it really was physically. So that's how we built the antenna on Sam's pacemaker. Designs. We actually tried more designs than that, but these were the two most successful. It was interesting what happened as we spiraled the antenna up, and I bet you can imagine. As the current starts to go down the antenna, it starts to couple to the nearby arms. The trouble with the spiral is that very large currents near the feed point coupled very quickly onto a nearby arm, and they basically made the spiral not act as long as it was physically. Sorry, the serpentine. Serpentine had that problem. The spiral was better because the coupling was not between immediately adjacent parts of the antenna. So our spiral design ended up being better than our serpentine design. Okay, so that's great, but the truth is the next generation of medical implants are going to be much smaller. I showed you a picture of the Utah electrode array. That's about the size we can expect next generation implants. And how on earth are we going to build an antenna on those tiny, tiny medical implants? It's probably unrealistic to actually be able to put the entire antenna on such a small package. So one of our ideas was to use the surface of the body to allow us to build a larger antenna, larger than the medical implant itself. That's kind of like a tattoo. You've probably seen tattoos on people's arms, and the tattoo is a nanoparticle that's held in the fat layer of the body. Fat doesn't move particles around as much as the rest of the body does, and that's why the tattoo stays present. The same thing could happen if we used or particles that are conductive and we print those in the fat skin. Oops, sorry. So if we a gold nanomaterial, it would be highly conductive. We could that fat layer, and the fat would act as an insulator, kind of a semi-insulator. So here's a picture of one of the nanoparticle antennas that we actually tested out. This is being tested on a piece of meat with rat skin with the fat. You can see the fat there under the person's thumb. And that antenna actually worked quite effectively to couple a few centimeters into the body to allow us to communicate with a deeper implant that was very small. So we used the surface of the body for the big antenna, and then we made a very small feed on the tiny feed. Now, we need a really good material for this. So we need a material that is conductive and biocompatible and isn't too solid. If it's really solid, like a wire, it would be great electrically, but it would be bad medically. So we are using a polymer that's thermally activated. This biopolymer starts out as a fluid, but when we inject it in the body, it turns into a semi-solid. The way it does that is it has a crosslinker, a chemical crosslinker that's held in little nanobubbles. As the nanobubbles break because of the heat, they release the crosslinker and allow it to connect the molecules together so that they become more solid. Now, this material is already in existence, but not highly conductive. So we can make a biopolymer that's thermally cross-linked today, but it's not highly conductive. So research that's being done currently in polymer science is actually likely to bring us the material. So if you're an antenna engineer, you might think, ooh, here's this cool material that might be coming in the next 5 years. How could I use it? So that's been the application that we've been working on in our lab. The material doesn't exactly exist today, but we're working on designs that could utilize it when it does show up just a few years from now. So here's a picture of the material. On the right, you see kind of a cloudy biopolymer material. We used a radio frequency cardiac ablation probe, which would normally be used to be able to solve problems inside the heart. It's a coax, it's just a piece of coax that is inserted into the vein or the artery, and it's pressed against the heart to heat, like you can see here on the left. It can be used to burn problem areas of the heart, or it can be used to remove plaque from arteries if someone is having problems with a heart attack, for example. We used this same probe and we put it inside our polymer. And as you can see here, we got some 3D solidification. We were pretty excited about that because it was a little uncertain if we were truly going to be able to heat this enough to make the material solidify. But in this case, you can see that it did. So we were pretty excited. So I talked about a tattoo antenna. That's good because it can use the large surface of the body, but we still have a medical implant that's deep inside the body. If the medical implant is very small, we wondered if there was a way of making a lens that would focus the power from our tattoo antenna in the fat layer down to the medical implant. So what you see here are two wires. Think of needles. Two wires. They are not touching a medical implant, but yet they are focusing the field. You know basic things about electromagnetics. One is that fields tend to focus on things that are pointy, on corners and points. And also we know that fields focus in small gaps. So a device like this that is pointy with small gaps is going to focus the fields pretty well, as you can see here. So our objective is to put an antenna that's tattooed in the fat layer to pick up the fields, and then to build a three-dimensional focusing lens like this to be able to concentrate the power down onto the tiny medical implant. Okay, well, we certainly could do this with needles, but no one wants needles left implanted inside their body. So we came up with another method. So in this case, we would use a coax, much like the radio frequency cardiac ablation probe. The coax would have a hollow inner conductor and would be used to inject the polymer where we wanted it. We would back out the probe while we heated it, producing a wire similar to this. So inject the coax, inject the material, back out the probe, heating as you go, producing the wire. So this is how we could produce a three-dimensional lens to support an implantable medical device. So now let's talk about another microwave space. There aerospace, most of them you will find military. So here is an example where a radar signal is hitting a jet, and you can see that there's a very distinctive pattern that's produced. This was calculated using computational electromagnetics. At the time, this was in 1995, this was one of the very largest computational electromagnetic simulations that have been done. Today, it would be considered a small to medium application. So considering radar and how it interacts with all kinds of devices is really a very interesting and challenging problem. Here is another picture of radar. It's hitting a horn or a horn antenna, and we're looking to see the horn and how much of it is carried around the outside. Another, I talk about entrepreneur. I'm going to move space. My colleague Jay Messina does simulate but the entire Earth and its ionosphere. So there are many space weather hazards that can cause problems with electric power grids, basically knock out the power grid. There are a number of resonances, there are geolocations, and there's detection of airplanes that have emerged in the ocean, in other words, that have gone down and been lost, and remote sensing of subsurface effects. So Jay Messina and her students do simulations using a spherical to be able to simulate how each of these effects work over the entire surface of the Earth and its ionosphere. Right in one of the areas fascinated with, and not long ago, I had a chance to visit the radio astronomy Arecibo Observatory in Puerto Rico as part of one of the IEEE Antennas and Propagation Symposia. You can see that there's an antenna held on, so the antenna is kind of right up here in the middle. It's actually a dual antenna that is transmitting or receiving a signal down here into this bowl. This is a large, it's like a canyon. It's an outdoor bowl. It's huge. It's concrete and it has around it. So this is one of the largest antennas in the world. It's used to receive signals from space. The signals come from space and bounce up to these antennas where they are picked up and turned into images of activity that you see going on in space. This antenna can be moved on these wires. This antenna is so big that it's about twice the height of a person. So radio astronomy is another of the really cool applications for electromagnetics. Another, I'm going to talk about Earth, the Earth part. I had a chance to do some sea ice measurements in Antarctica and the Arctic, and I just want to talk a little bit, just for fun, about engineering invention and what it feels like, the experience of that. So let's start with a really tough question, and that's sea ice and climate change. You can see, and we are familiar with the fact that sea ice is going away. The challenge is that all of the models that predict sea ice loss underestimate the amount of sea ice loss. We don't fully understand what's going on. Now, one of the reasons that this might be underestimated, I'll be showing you, is sea ice is a really interesting material. It's heterogeneous. So it has different material properties horizontally and vertically. It's not just a simple piece of ice. It's a special kind of ice. The reason it's special is brine inclusions. As the sea ice freezes, the salt tends to stay in these little puddles and the purer water on the outside freezes. So these brine inclusions are several millimeters across or even much bigger. So you can see this structure that looks kind of like a tree. That's actually brine inclusions inside the sea ice. Now what those brine inclusions do is they allow fluid, literally water, to pass through them. They kind of act like tubes or pipes. This is a CT image of the brine inclusions, and you can see that they tend to elongate in the vertical direction because of gravity, but not so much in the horizontal direction. So if you poured fluid, sea ice like this, you can see that there are actually going to be some channels where the sea ice will drip through very well and other places that it doesn't. Okay, so if we are really interested in how much fluid can move through sea ice, we can also do that electrically. So I'm going to go back one slide. If I had water here on top, there are places that it would almost flow all the way down. There are these things called melt ponds, start in the spring, and they are these ponds over the surface of the ice, and then suddenly they disappear. Like over 5 or 10 minutes, the entire pond, the entire lake disappears back down into the ocean because these channels will allow the water to go through. Now, these channels are basically salt water. So if they are salt water, we know they are highly conductive, whereas the rest of the ice is low conductivity. So we can measure the fluid material, the fluid properties, using the electrical properties. So right here, here's the relative permittivity and conductivity. So we need to know both the real and imaginary part of our relative permittivity, and it's different in the horizontal and vertical direction. So we went to Antarctica to visit this, to measure this. And this was on the left, you can see us in New Zealand before we left. And then just a few hours later, we were in Antarctica, where I can assure you it was much colder. This is flying over the continent of Antarctica. It was pretty magical to see this out of the window of the plane. Here we are at Scott Base. It was me and my graduate student, David, and it was Ken Golden, a professor of math, and his postdoc, Joyce. Here's the rest of the research team. It was a large international research collaboration. We lived in those green boxes for about a month, and our car was this yellow thing called a Hagland on the left. Up on the top, you see these things that are used to get over cracks in the ice. You'd lay those down and drive the Hagland over the top. So here's our office right there. Back office, you can see our houses were these green storage units. You see me here talking on a satellite phone. That is the only communication that we had. And then our beds were here. There, four of us slept in each storage unit. This is how we got our ice. We used a ice core driller. Ken is using it here on the left, and you could ice held by one of our New Zealand friends here. So our goal was to measure the electrical conductivity in both the horizontal and vertical directions. So the first thing that happened as we came into camp is we plugged in some of our devices, which were US devices, plugged into New Zealand power, and we promptly blew the fuse. Yeah, we had to fix that. We tried our DC measurements. They didn't work well. Our temperature probes corroded. So basically the first day, nothing worked. The second day, here's our resistance meter. We put nails in to make connection with the ice. Not very much worked, and in fact, you can see we had lots of problems cracking our ice. So the second day, not very much worked. Does this sound like an engineering experience to you? The second day, however, we were able to figure it out. We started doing some basic experiments again. We put resistances in between our test systems, and we were able to figure out how to make it work. So by day 3, we had a little success. We finally were able to get our measurements to work. Okay, so we were able to get vertical measurements by day 3. Now day 4, let's try getting the horizontal measurements. So we tried this method. It didn't work. And we tried this method, and it didn't work. And we tried this method, and it didn't work. And we tried this method. It kind of worked, but not very well. So we tried this method. It kind of worked, but not very well. And we tried this method, and it kind of worked, but not very well. I hope you're getting the message here that things don't work the first time in engineering. You just have to keep trying new things until you can make it work. So after filling up 4 lab notebooks, testing in this kind of environment, we were joking around. We were actually teasing Ken because he could never drill straight. We were teasing him, Ken the crooked corer, Ken the crooked corer. And then it occurred to us, if we actually drilled our cores at an angle, crooked on purpose, we could measure both the horizontal and the vertical parts of our core from one single core, and this method worked. So here are the important messages. Things go wrong. Inventors solve problems. When it goes wrong, fix it. When your fix doesn't work, try again. Think and try and think and try, and don't forget to play. Inventions and solutions happen when you least expect it. So engineers think, invent, try, and fix it. So now let's talk a little about high-speed circuits. This is an area that a lot of our students are starting to get significant work in, as the speed of the circuit so high, fields no longer stay right on the lines. They act a bit like antennas. So here is a model of a high-speed circuit, and you can use this model, these measurements, to be able to tell where there is a problem with either the electromagnetic compatibility, this circuit might be interfering with something else, or the signal integrity. This circuit isn't doing what it was supposed to do. So signal integrity is one of the cool new areas that a lot of our students are working. Now, it's a time when we have COVID. I know that. It's a time that many of our engineers here in the United States, and I believe internationally, are finding it more job because there's a financial challenge. This is a problem time. So I wanted to share with you a message about, if you can't find the job you want, you may need to make your own job by being an entrepreneur. So engineers have been very successful in business. These are the CEOs of Fortune 500 companies, and you can see that the largest number of these CEOs have degrees in engineering. So let's talk a bit about starting your own business. It's quite an adventure. So we're going to talk about why, who, how, and what to do next. So this is a picture of our team in 2002. We had built a series of pretty clunky little boxes that were able to do something pretty cool, but this was hardly a company, but it was a good idea. So at this stage, we had a good idea and no company. So the goal of this company is to solve serious problems. You don't find a good company without a serious in the background. The problem that we were after was that electrical faults in flying vehicles, such as, here's the space shuttle, 7 seconds into flight, the main engine controller shut down. And the reason it did was because one of the wires had vibrated and touched some metal sections of the plane. Now, the fact that that was making such a bad short circuit, I hope somebody picks up that phone for me. The fact that that was making such a bad short circuit is what made the engine controller shut down. This problem happens in airplanes too. This is an example of an arc fault. So we have just a little bit of dampness across a couple of cracks in wires. They can actually make a flashover that turns the electrical insulator of the wire into a conductor instead of an electrical insulator, and the thing explodes. That, as you can imagine, is pretty bad. So the goal of this company was to be able to locate problems on these wires while the plane or the space shuttle or whatever is live and running. So why is that important? Here's an example of an arc fault circuit breaker. You can see on the left that if a regular thermal circuit breaker was used, that many of the wires basically blow up when you have a fault of this type. But if you use an arc fault circuit interrupter, you get a much smaller problem. That's great because it reduces the risk of fire and it improves, but it's also a big disadvantage because the fault on the right, which is good because it's safe, it's too small to locate. Almost impossible for the maintenance person to find this problem after the plane has come back down to the ground, safely, of course. Now, the goal of this company was to say, that little fault right there was a short circuit for a very short amount of time up in the air, and we need to find it while it's a short circuit because we can't find it when it's down here on the ground. So we're using this method that we invented called spread spectrum time domain reflectometry. It's kind of like radar, but it's for electrical wires. So an incident pulse is sent down the transmission line and a reflected pulse comes back. That's standard reflectometry. The delay between the pulses tells you where the fault is, and the type of pulse, whether it's positive or negative, tells you if it's an open or a short. So spread spectrum time domain reflectometry works this way. It uses a pseudo-noise coded signal. That's like the signal from your cell phone. And it's square wave modulated using a square wave signal generator, and that's put together into the system. It goes down the wire. Let's see if I've got this. Yes, the incident signal is put into the wire, goes down the wire where it reflects back, and then it's correlated. And I'm going to see if I can. It should be able to play this video, I hope. Oh, nope, the video play. Shoot, I'm sorry, this video won't play in this version. Sorry. So what it does though is it takes these two signals and it correlates them against each other, and I get a large correlation when the two red dots match up. Okay, so that's a good idea. And at that point, it was a technical idea with no company. Then we needed to figure out where we might put that inside, in this case, an airplane. So we had this idea called a smart connector. We thought it would be really great if you had a problem with the wire and you could put this electronics here in the connector and be able to put in the smart connector, put the wires back together, and that would test your plane. Well, that was a really good idea, except it wasn't. The challenge with the connectors in aircraft, every single one of these connectors has a special key to it. There are things that are kind of poking out here that make it put the wrong connectors in, which means every single one of those connectors would have had to be custom made for every single set of wires on a plane. That's how we learned about. We needed to figure out who customers were, our distributors, industry reps, regulators. We needed business experience. We needed someone with money. We needed legal, taxes, project management, directors. 2 universities were involved, and here was our little engineering team. I can assure you that all of these jobs are too big for the 6 of us, and so we needed much more help in order to really start our company. The first thing we needed to do was figure out who our customers were. Were they the maintainers? Were they the person that owned the planes? Who were our customers? So we developed this method. It's called the lean canvas. The lean, but we actually developed it for doing an invention. The first thing you have to do is identify your problem. We had found our problem for sure, but we also needed to know about all the different stakeholders that were involved in this problem and what sort of standards and regulations we needed to be able to work with. We then needed to come up here to the types of problems, like why was a practical problem not solved? What gap existed? So we did a literature review as well as a patent review, found solutions, and learned a lot about the market. We needed to figure out what was novel and why the special features were going to be important. That question, methodology, and so on until we finished our outcome. The message here is businesses are not actually put together randomly. You really need to do your research and your homework in not only the solution, but also the business environment in order to be successful. So from our first board, this was my PhD's final project for his dissertation. We moved into a handheld device here. Actually, our first smart connector. Remember the one I showed you? So here's the smart. The second chapter, getting smaller, we built a chip and we ended up building a series of box handhelds and embedded materials. So from 2000 to 2020, there have been a whole series of changes in what our customers needed and what we understood our customers needed. Now, I mentioned doing this for aircraft, but our successful application to date is actually rail. This is being throughout the British rail system to be able to handle the control lines that control the rail system. So let's talk a bit about the money part of a company. You need someone to invest in you so that you can actually build these things. So I want you to imagine that you are a venture capitalist who might have money that could invest. What would be the most important aspects of your team? Would it be the quality of your management team? Would it be growth potential, the return on investment, the size of the market? All those are important. Or would it be the engineering, the proprietary uniqueness, or the brand strength of your products? So just think in your mind right now, which of those do you think is most important? I'm going to show you what most entrepreneurs think is most important. Most entrepreneurs think it's the return on investment, and that's what the venture capitalist is most looking for. But the venture capitalist will tell you that it's the quality of the management team because that's what will lead to the return on investment. So suppose that you are thinking of starting your own company. There are 10 essential skills. Passion and energy are probably the two most important because this does take a lot of energy. Vision and perseverance are very important as well. You really have to know where you are headed and you have to keep going that way. Patience is important. I've been at this for 20 years. Communication. So I know you're taking engineering classes, but how about the classes that help you write and the classes that help you speak or present? Those are very, very important as well. And then people skills, Psychology 101, being able to manage people, work with all kinds of clients and partners is really, really important. And then appropriate risk taking. So being able to take risks, but not outrageous risks. So being able to make your risk taking appropriate. Leadership is important as well. And did I say passion? That would clearly be the single most important thing. So why might you start a business? It might be to make money, for prestige, but the reason I started a business was to make a difference and to be able to bring a solution to the many problems that were happening in aerospace. So, graduate school. Enjoying this presentation, and I hope that you might be in the University of Utah about coming to graduate school when you finish your undergraduate degree. So, why just this is one of my engineering teams. So working together to solve live problems is just plain exciting and fun. It's just invigorating to get up in the morning and work, often struggle, through problems together. Inspiring the next generation is one of the delightful things that faculty get to do. These are two students who were high school students. They now both have master's degrees in engineering. And so being able to work with them and inspire them to go on was very, very exciting. Love your work and love your life too. Having a graduate degree and that level of prestige, knowledge, and enjoyment is really very valuable and very enjoyable. And then I put this one in because engineering does not have to be your average desk job. If you want to get out and truly have adventures, boy, this engineering degree has taken me there. Design things that matter. I actually went into engineering to change the world after I learned about the earliest MRI machines. And this was the earliest prototype of that coil that I showed you in the previous picture. This is one of our graduate students, and no, that's not his hair. Those are cables with SMA connectors on the end that we were using to test out this earliest coil. reason, the opportunity to travel. I bet some of you recognize at least one of these pictures. So being able to see the world and visit people in all parts of the world has been incredibly exciting. So engineering is about being a creative problem solver. It's like finding a problem. Here's my cat trying to get the fish, but she can't reach around the edge of the stairs. This cat never did get the fish, but she worked really hard in trying to do that. So be a creative problem solver. That's what engineers do. So now I'm going to share advice. I've had many mentors. I hope you find mentors in your life too. We don't do this alone. Clear back in junior high, my shop teacher said, "It will be hard, but you can do it." My physics teacher in high school was the one who said, "Hey, have you thought about engineering?" My bachelor's and master's advisor, Magdi Iskander, was demanding, and he said, "No, it's not right. Fix it." So we were constantly fixing things. My PhD advisor, Gandhi, would say, "Well, that is very interesting. I wonder why it's like that." So that's what engineers do. We wonder why. One of my first professors, Carl Durney, encouraged me to come sit down in front in class and said, "I think you are underestimating what you can do." And have chocolate cake every time you have dessert. Rand Chair said, "Write bigger proposals." And Constantine Balanis, you might know him from it, said, "This is Dr. Furse, and I think she would just be great for." The message there is we always have to help each other move up. And Maria Stuckley, do it in heels and be who you are, really. Tom Parks, make sure your leadership always has quality. Richard Felder, teaching matters. Now, I know that I've done a lot in antennas and propagation and electromagnetics, but I want you to know that I haven't, and you don't need to either. Look for good mentors. Look for people who help lift you up, and look for people that you can help lift as well. So who's our next mentor going to be? It all depends on the question. So I want to say thank you to my team. These are some of my students. And this website that I've, oops, oh shit, I made it go away. But right here, you can find many of our publications linked there as well. So I hope you've enjoyed this presentation. I've enjoyed getting to come and visit you today, and I'd love to know what you have for questions. So I'm going to hit the chat box and take a look. So let's see. Will I share the slides? I'll be glad to try to send them to your professors, and then they could send them with you. They could share them with you. Do you have any questions that I could answer?
Okay, there is one question from Mahima that are the Utah electrode array and DBS being used in today's world? She's asking. Is still used? Yeah.
Okay. Is the Utah electrode array and deep brain stimulation active today? The answer is yes to both of those. Deep brain stimulation has been a routine treatment for Parkinson's disease for almost 10 years. It's being used for many other things more experimentally, but it has been very successful for Parkinson's disease. The Utah electrode array has been implanted in a number of people for a number of applications, but it has not had a full wireless interface to date. Okay, I see another question about opportunities in microwave tubes. Microwave tubes have been around for a really long time, and so some people think that anything that can be done with tubes has been done with tubes. I would strongly disagree. I think you'll find a number of applications for microwave tubes in the radar industry, as well as all high-powered electromagnetics. Much of that shows up in military applications, so that's where probably most of the jobs in microwave tubes are. There are some in medical as well, but I'd say most of them are probably in military. So let's see, applications in electromagnetics that relate to artificial intelligence and machine learning. That's an excellent question. There are numerous applications in electromagnetics for artificial intelligence. So for example, when we first started building antennas, I showed you the implantable antennas that were the spiral and the serpentine. We also built an antenna called a genetic algorithm antenna. Genetic algorithms is just one artificial intelligence possibility, where we were able to make the antennas much better by letting the machine figure out what the best antenna could be. Similarly, artificial intelligence and machine learning are now routinely used in medical imaging of all kinds, including MRI and CT and microwave imaging. So there are many applications for that. Radar also has strong artificial intelligence algorithms that have been implemented into most realistic radar systems. So there is a lot of artificial intelligence that's used. Excellent questions. Thank you so much.
Okay, so there is one question from my side. Initially you started talking about the effect of this mobile communication on the brain. So currently there is a lot of talk going on about how this 5G is going to affect the brain and how it affects human bodies. What is your take on that? Have you done any research or anything on that area, like how 5G waves are going to affect, because the frequency is going to be very high. So how do you see that?
That is a very good question. So the question is, how is 5G likely to impact the human body and the brain in particular? So although I have not done specific simulations for 5G, I have looked at this literature, as probably many of you have as well. There are several things to remember when we are considering what's likely to happen here. First of all, 5G is higher frequency. We know that higher frequencies penetrate less into the body, not more. So it is unlikely that the 5G energy in any application can actually get to the brain. So the brain is probably the area that's, reasonably protected with these 5G signals. Now, the concerns have been more about, are there small aspects in the skin? Are there sensors that we don't know about in the skin? Because really the 5G signals are pretty much limited to the skin and fat region. And although biologically we don't think that these types of sensors exist, definitely people are looking to see if they might be. So you can never prove that anything is safe. You just can't in science. You can never prove something is safe. You could prove it's dangerous, but we aren't seeing any cause for danger yet. The other aspect of electromagnetics to remember is that when we talk about electromagnetic radiation, it is a non-ionizing radiation. It is very, very different than X-ray. So it's not the same thing. Not even the physics is not the same as X-ray radiation. So micro radiation is not breaking cells. It's not damaging cells. It acts in a totally different way. We could worry about microwave radiation or 5G or any other type of radiation if it was strong enough to cause heating, because heating does damage cells. But in the case of wireless technology, it's unreasonable to expect that we would ever be at levels high enough to cause heating. So you can look through the literature yourself, as I would strongly suggest you do, but I think that 5G appears to me to be less dangerous than any of the lower frequencies because less of that power is actually going to go into the body.
Yeah, thank you. So one more question is, so you were talking about entrepreneurship and the innovations. So you showed that when you started in 2000 and you came up with a lot of changes, and till 2020 you had a lot of changes in the product. So I know that in the market things keep changing. So how do you keep up with that, and how do you innovate your product to keep up with the challenges and the expectations from the current trends in the market? How do you do that? Because you start with an idea and then you go on with over a decade, everything changes in the market. So how do you tackle that?
Oh, that's a super good question. How do you keep up with the changes in the market? Let's expand that question to how do you keep up with the changes in the market and the science and the technology and everything that's happening so fast in engineering through the entire world. It is hard to keep up, but it's fun to keep up. So we read a lot, journal articles, and we go to conferences a lot so that we're visiting with people and finding out more about the work they're doing. Every time there's a good IEEE workshop, like this one right here, I love to attend those. So talk to people, read about things that they are doing, and keep up with that technology. This is the challenge of an engineering job. You learn so much through your bachelor's degree. I mean, it's intense. You learn a great deal of information, and then you leave school and you think your learning's done. It's barely started. So just keep reading, attending conferences, and talking to people, and continue to learn. Also realize you cannot possibly know everything. And so surround yourself with lots of good people who know things that you don't know. Look for people who are different than you and have different backgrounds and experience, and continue to work with them so that you can learn from them as well. Don't expect to know everything, but you can know everyone. That will help you. Now, how does a business keep up? A business has to be customers. They have to be the people that their customers turn to with questions. And probably the biggest challenge is listening to your customers. So many businesses will hear from their customer and go, yeah, yeah, we've got a solution for that. I say stop and listen to your customer. They are going to tell you what's going on, and they're going to challenge you. Absorb their knowledge and experience and try to find better ways to help them in the future. So, as engineers and business people, we have to be constantly changing and updating and keeping up. It's a challenge, but it's also so much fun. So, I see another note about the 5G on the chat box, that as the frequency increases, the power density in a squared unit of area is less per FCC regulations. And in that case, 5G is not a problem. That is true. And that's just because as the frequency increases, it doesn't penetrate as far into the body. And so the fields are smaller. I see another good question here on what materials are preferred for implants. That's a really good question because that is changing constantly as well. Most of the metallic parts of the implant are either titanium or gold because those have the least interaction with the body. So the way they tell about interaction is they put the material in the body, and then they put the material not in the body, but in like a petri dish, and they heat it up and they just see if the molecules penetrate out into the petri dish. Gold and titanium are the two that penetrate the least. So those are really good metallic materials. The insulators, we have a number of plastics and ceramics. Teflon, for instance, is perfectly good in the body. So there are a lot of really good solid insulators that can be used. And then the materials that I'm really interested in right now are the polymers. And the polymers already, there are a number of conductive polymers made with gold nanoparticles. And there are a number that are made with carbons, although they don't seem to be as good for biocompatibility. Polymer science is one of the areas that's just rapidly increasing. So we need to watch that area and use those materials as they come out. So let's see, I'm trying my box. Let's see the additional questions. Okay, statistical processing. So someone asked, other than antennas, have I worked in statistical signal processing? Problems in microwaves relate to statistical signal processing. So I haven't done a lot in statistical signal processing, other than, of course, the SSTDR application put together very much like a one-dimensional cell phone. And that was pretty cool. So the other aspects of using this in statistical signal processing that I've done has been that there are additional signals on a live system where we are running SSTDR. And so using statistical signal processing methods, we are able to pull our SSTDR out progressively better. So that's cool. In electromagnetics and microwaves, you find all kinds of things in wireless communication. which is where you're going to get some of the statistical signal processing and also in imaging. So both in communication and imaging, I think you'll find more of the statistics. Okay, here's a question about what is the life of the antenna and does its performance degrade? The answer to that is absolutely. In biological materials, the antennas are inclined to degrade because they'll get covered by scar tissue, which basically insulates them. They can get covered by scar tissue, they can deteriorate themselves, and their connections always corrode. So antennas in harsh environments like the human body or subsurface like under the earth or in water, all of those antennas tend to degrade. It's really hard to keep them from degrading. So yeah, antenna performance is inclined to degrade over time. So does cable performance, and all connectors are evil. Anytime you have to put a connection into anything, you know it's going to corrode and be damaged in other ways as well. So the fewer connections we have to have, the better. Well, thank you very much for all those really great questions. Are there any more that you'd like to talk through?
Kirtipriya, madam, can you just see the Q&A box? There are some questions.
Okay. All right, I see one more.
Yeah, so in Q&A box, we have few questions. So one question is, what is the significance of algebraic topological method in computational electromagnetics?
What is the significance of what in computational electromagnetics? Please repeat it.
Algebraic topological method, ATEM.
Boy, computational electromagnetics is so broad at this point that computational electromagnetics is already a very mature field, and we have many excellent tools. However, there are still a lot of problems that are difficult to solve perfectly or even very well. So each of the newer computational methods that you see will typically be in response to some kind of challenging problem. And we keep hoping, it's kind of a bad hope, we keep hoping that our existing tools will solve every problem that we want to do. But as soon as you start using these tools, you discover, nope, I need something that's a little thinner, a little fatter, a little more anisotropic. There are new challenges for every one of our tools. Someone posted a question about stochastic FDTD, which is one of the areas we developed. Finite difference time domain, for example, has been around for a really long time, but it's not able to solve problems that are statistical. For example, that the electrical properties of the body vary slightly from person to person and even time of day to time of use a statistical approach to evaluate how much that would affect our fields. So the only reason kind of to use another or develop another computational method is when you find yet another problem that today's methods can't fix. Okay, let's see.
Yeah, there's another question. What is your opinion on 5G frequency absorption, specifically in skin layers? What should be the research direction now to investigate the biological effects?
That's an interesting question. So, what kind of research should we do now with 5G to find the biologic effects? So, what happened with the original frequencies, the 950 megahertz frequencies, is electromagneticists predicted how much power and what type of power was in what location, but biologists had to figure out what kind of medical effects that could have. The same thing needs to happen now. So electromagneticists need to simulate well how the 5G fields interact with the head, the eyes, and any other part of the body, but mostly head and eyes are what we're worried about. So we need to predict, in this case, I would say not only the magnitude of the fields, but also their time varying properties. Because if they are high frequencies, they're varying very quickly. And then biologists need to do kind of petri dish experiments first and be able to tell if we have a field of this type, what kind of things does it do to cells? Now, the challenge there is also interesting that we can use, let's say, a cell phone, and we put it next to a head and we get a certain amount of power someplace in the head. If we held the same cell phone next to a petri dish, the amount of power would actually be different. So developing systems that can radiate something simple like a petri dish in the same way that a cell phone might radiate the head, being able to develop those systems for biologists to use in their testing is one of the areas of research I think would be pretty cool. And then, of course, the biologists need to do these tests. Now, in addition to doing direct biological tests like that, there's also a good deal of epidemiological research where people will just watch the statistics of disease in a population and see if that changes as we bring on 5G, for example. The studies on cell phones have shown there really hasn't been an increase in disease since we've had cell phones. So that kind of means there's probably not a biological effect that is deleterious to the human body. So there is a lot of research yet to be done.
There is one more question. Can integrated optical devices be used for implants? Since if they are made of silicon, can integrated optical devices be used for implants?
That's a really interesting question about if integrated optical devices could be used for medical implants. There definitely have been methods that have been proposed with optical devices. If you have something that's very close to the surface, the skin is partially transparent, and so optics can be used for that. So that's one definite possibility. A second is, you see how we're building like this polymer material, and the polymer material is kind of clear. Could that be used as an optical transition into the body? Very possibly. So there are some devices already that use optics close to the skin. There is nothing that I know of that goes deep, although I could be wrong. There's always so much new stuff. But yes, it's possible in the future, and yes, some exist today.
Thank you so much for all your answers. I think that's all the questions we have. So, Dr. Mahesh, would you like to take over?
Yeah. Thank you very much, Dr. Cynthia Furse, madam, for elaborately covering all the applications, starting from medical implanting antennas to aerospace applications to micro integrated circuits, and for your inspirational words for students as well as for the research community in antennas as well as electromagnetics. I would like to thank you for your wonderful lecture, for your time and your dedication in the field of electromagnetics and antennas. You are like inspiring personality for all the students as well as researchers for carrying out the work in antennas and microwaves. From IEEE Bangalore section side, I take this opportunity to thank you for your time as well as delivering this wonderful lecture. Thank you very much, madam.
Thank you for hosting me. Thank you very much.
Yeah, thank you very much. I thank all the participants for attending this webinar. Thank you, Kirti madam, for helping me to host this webinar. Thank you very much. We'll close the session. Thank you, madam, once again. Thank you, professor.
Okay, thank you. Thanks a lot.
Yeah, good night. Good night. Good night.
Good night.
Good night.
Madam, we'll close the meeting.
Yes, so you can stop the recording.